possibility that they will collide in the future. A merger could trigger a burst of star formation, but it could also destroy the ordered structure of the spiral arms, transforming the system into an elliptical form. Such events often lead to chaos in the internal dynamics of stellar orbits and fundamental changes in morphology. If this formation becomes part of a larger galactic cluster, the pressure from the surrounding environment may strip it of its remaining gas, completely shutting down star formation. In that case, it will become a fainter and more passive system where stars age without new generations replacing them. Observations suggest that this stellar island is surrounded by a vast dark matter halo. This invisible substance holds the galaxy together, preventing its stars from drifting apart. The question of how dark matter is distributed and what properties it possesses remains one of the greatest mysteries in modern astrophysics. Some theories suggest that dark matter consists of dense clumps, influencing the motion of stars and gas. Other hypotheses propose that dark matter interacts with itself in ways that we have yet to detect. Over time, the galaxy will become dominated by stars that have reached the end of their life cycles. White dwarfs, neutron stars, and black holes will gradually replace the younger, more luminous stars. If star formation ceases entirely, this world will, in trillions of years, become a place populated only by the faint remnants of once bright celestial bodies. Beyond internal factors, the system's fate will also be shaped by the evolution of the universe itself. The expansion of space is gradually increasing the distances between galaxies. If this process continues, then in the far future, surrounding objects may disappear beyond the cosmic event horizon, leaving this stellar world in complete isolation. The question of whether this galaxy could ever become home to intelligent life remains unanswered. If life arises within one of its planetary systems, it will encounter conditions different from those found in our own galaxy. In an era when bright stars fade, civilizations may search for ways to harness the energy of white dwarfs, neutron stars, or even black holes. Perhaps, in the distant future, advanced technologies will emerge that allow civilizations to manage energy resources on a galactic scale. This stellar world is one of countless objects in the universe, each a dynamic system evolving over time. Its fate could take many paths, retaining its current structure, transforming into an elliptical system, merging with other formations, or becoming isolated due to the expansion of the universe. But no matter what its final destiny may be, it remains part of the continuous cosmic process. Every star, every gas cloud, every gravitational force is a link in the great chain of the universe's evolution. We have only begun to uncover this story, and many discoveries still lie ahead. As observers continue to study distant galaxies, each new detail becomes part of an endless exploration that will never truly end. As time passes, this vast galactic structure will continue to change, shaped by both internal and external cosmic forces. While the present era is marked by active star formation, powerful stellar winds, and dynamic interactions, the distant future will bring a more gradual transformation. The balance between creation and destruction, between the birth of new stars and the fading of the old, will alter how this system evolves over billions or even trillions of years. The slow depletion of gas will lead to a decline in the birth of bright, massive stars. The spiral arms, once vibrant with nebulae and young stellar clusters, will begin to fade as fewer new to replace those that die. The remaining gas will become increasingly diffuse, spread thinly across the galaxy, no longer able to collapse into dense clouds that fuel star formation. no external in from intergalactic space, this system will slowly transition into a quieter, less active state. While the visible structure of the galaxy undergoes these changes, its invisible dark will continue to play a crucial role in its long-term evolution. The unseen gravitational framework that holds the stars and gas together may influence future mergers, interactions, and even the galaxy's eventual fate. Some theories suggest that dark matter halos are not static but may evolve over time. Possible galaxies like this one maintain their structure over cosmic timescales. As the number of new stars decreases, the population of stellar remnants will grow. White dwarfs will become the dominant stellar type, gradually cool over trillions of years. Neutron stars and black holes will also become more common, remnants of the stars that once illuminated the galaxy. If enough black holes exist within the system, they may begin to interact gravitationally, forming dense clusters or even merging into larger structures that could eventually fall toward the central supermassive black hole. Over billions of years, the galaxy may undergo a transformation driven by gravitational interactions with other systems. If it merges with a neighboring galaxy, it may lose its spiral structure, becoming an elliptical system where stars move in more randomized orbits. Such a transition would mark a major shift in its evolutionary path, reshaping the way stars and stellar remnants are distributed throughout its volume. In a more extreme scenario, if the galaxy is absorbed into a massive galactic cluster, it may experience what is known as ram pressure stripping. This process occurs when a galaxy moves gas that fills the space between galaxies in a cluster. The pressure exerted on the galactic medium can strip away any remaining gas, effectively halting star formation entirely. This would leave behind a system composed mostly of aging stars, gradually fading over time. Beyond these local events, the larger scale evolution of the universe itself will influence the ultimate fate of this galactic giant. The expansion of space, driven by dark energy, is accelerating. Acceleration definitely, galaxies will become increasingly isolated, drifting apart until they can no longer interact with one another. Over time, they find itself alone in an expanding void, with no nearby galaxies left to merge with or draw gas from. In the far future, as the last remaining stars exhaust their nuclear fuel, the galaxy will enter its final stage. White dwarfs continue to cool, dwarfs, cold, dark remnants emitting no light. Black holes will persist, slowly evaporating through Hawking radiation, though this process takes an unimaginably long time. Over an almost inconceivable timescale, the galaxy itself may become a vast, dark collection of degenerate, silent and unchanging. But even in this distant future, the story of this galaxy will not truly be over. The fundamental forces that shaped it, gravity, dark matter, cosmic expansion, will continue to operate. New discoveries may one day reveal unknown processes that influence its fate in ways we cannot yet predict. Perhaps advanced civilizations, if they arise and endure, will find ways to manipulate stellar remnants, harnessing the energy of neutron stars or even black holes to sustain life long after ordinary's burned out. For now, this galaxy remains a vibrant and active luminous beacon in the cosmos. Its arms swirl with gas and dust, its stars shine brightly, or harbors the powerful force of a supermassive black hole. It is a system still in motion, still evolving, still participating in the grand, ongoing story of the universe. And as we continue to observe it, to study its future, we are reminded that the universe itself is not static. Every galaxy, every star, every atom is part of an endless cosmic dance, a process of change and transformation that spans across time and space. This galaxy's story is far from over. It is just one chapter in the ever-unfolding narrative of the cosmos, a reminder that, in the vastness of the universe, there is always more to discover. The cosmic clock continues to advance. The evolution of this galactic titan will be shaped by forces both predictable and mysterious. What we observe today is vibrant and full of energy. The deeper laws governing the universe ensure that no celestial body remains unchanged. Over unimaginable timescales, this stellar system will transition through different phases, each marking a new chapter in its vast history. The present moment, defined by the ongoing formation of stars, will eventually give way to a quieter era. The great nebulae that now serve Aries will slowly disperse, leaving behind only that have already formed. Without a steady influx of cold, no new generation to burn out. Line will be gradual, barely perceptible over human life over billions of years become clear. The galaxy's arms will fade, the glow of massive blue stars, and only long and cooling remnants will remain. While the visible galaxy change, unseen processes continue to influence. The dark matter halo system will persist as a gravitational scaffold shaping the Mars even after the loss of its brightest members. Some theories suggest that interaction with matter halos could lead to subtle, long-term effects on galactic evolution, possibly altering the way stars orbit or influence mergers in ways not yet fully understood. Even as the galaxy settles into a more passive state, the remnants of brilliance will still be present. White dwarfs will form a vast population, each a dimming ember of a once luminous star. Neutron stars, the collapsed cores of the most massive stars, will rotate, some still emitting faint pulses of radiation. Black holes, formed from the depths of the heaviest stars, will drift through the system, invisible but ever-present, exerting influence. The central superpole, now dormant or only occasionally active, will remain as the galaxy's silent. Over time, continue to gain mass through fusion or by merging with other black holes, should galactic interactions bring new material into its. If the system experiences nature, this black hole could awaken once more, unleashing powerful that briefly reshape its surroundings before fading into darkness again. The law of the galaxy is also bound to the broad of the universe itself. If cosmic continues at its current accelerating rate, galaxies will drift further apart, severing their connections to the larger stars belong to. Even the faintest traces of other galaxies will recede beyond the horizon, leaving this system alone in an empty cosmos. Without new interactions to provide fresh material, it will continue its slow transition into darkness. In the deep, when trillions of years, even the stars will begin to fade. Red dwarfs, which burn extreme efficiency, will eventually exhaust their reserves, leaving behind a universe filled only with. The galaxy will become a place of silent white dwarfs, neutron stars, and black holes, drifting endlessly through the void. Even these objects, given enough time, may meet their end. White dwarfs will cool to black dwarfs, emitting no heat or light. Black holes, the most of all, may slowly the slow process of Hawking ray vanishing into the vacuum of space. Yet despite this seemingly inevitable decline, the universe remains a place of possibility. If advanced civilizations arise within the galaxy, they may develop ways to harness the energy of its remnants, new methods of survival long after the stars have faded. Technologies beyond our current imagination, life to persist, adapting to the cold, dark universe that will one day emerge. For now, however, this galaxy remains alive, its stars burning brightly, its spiral arms stretching across space, its black hole holding court at the center of a vast and complex system. It is a place of ongoing transformation. Forces play out on scales intricate. Every supernova, every drifting magnetic field tells a story written in the language of the cosmos. As we continue to study it, we are reminded that the universe itself is static. It is an ever-changing tapestry of matter, energy, and space-time, each moment in an infinite sequence of events. This galaxy's journey over, it is simply continued cosmos, and as long as to look toward the stars, its story will continue to written across the fabric of time itself. The journey of this galaxy through the cosmic expanse continues, an unceasing progression through the vast, uncharted time. Form is defined by swirling arms of stars, luminous nebulae, and a dynamic interplay of nature will see it undergo transformations that stretch beyond the scope of current understanding. Each station is part of a grander cycle, growth are inextricable. Even as the light of new stars fades, the underlying gravitational structures will endure. The stars that once illuminated the galaxy will drift through a steadily dimming sky, bound to their orbits by the unseen mass of dark matter. Over eons, these orbits may shift due to subtle gravitational interactions, causing some stars to migrate outward while others spiral inward to a black hole. In some regions, dense stellar remnants may cluster, forming compact systems of white dwarfs, neutron stars, and black holes locked in a slow gravitational dance. While large-scale interactions will become increasingly rare as the universe expands, this does not mean the galaxy will remain entirely isolated from cosmic events. Rogue objects, free-floating planets, interstellar debris, or even intergalactic stars ejected from distant collisions, may pass through its boundary local dynamics in unexpected ways. Occasionally, binary systems may undergo disruption, one star outward at immense speeds while the other falls into the depths of a black hole. These rare events will provide brief, long, gradual shift toward equilibrium. At the heart of it all, the central black hole will persist as the galaxy's gravitational anchor, long after its brightest stars have faded. If no further matter is available to feed it, it may remain dormant, a dark monolith at the center of a dying system. Yet in the event of a galactic merger, even in the distant future, it could awaken once more, consuming stellar material and releasing vast amounts of energy in a final display of activity before the universe grows too empty to sustain such processes. On the longest timescales, when even the most enduring stars have obscurity, the galaxy will be reduced to a vast collection. White dwarfs, once the glowing cores of sun-like stars, will cool until they no longer emit any heat or light. Neutron stars, relics of past supernovae, will persist as silent, invisible spheres of dense matter. The ultimate endpoints of stellar collapse will remain scattered across the galactic remnant, their presence detectable only through their gravitational influence. Yet even black holes are not eternal. The slow process of Hawking radiation, a quantum effect predicted by theoretical physics, will cause them to lose mass over unimaginable timescales. As the of the universe unfold, these black holes will gradually evaporate, releasing their remaining energy into the darkness. Eventually, after a period so long it defies human comprehension, the last traces of what was once a grand and thriving galaxy will dissipate, leaving behind nothing but the vast, empty expanse of space. But even in this apparent finality, the story of the universe itself may not be over. Some theories suggest that new physical processes could emerge in the distant future, leading to the birth of entirely new structures, new galaxies, or even new forms of matter and energy. The eventual fate of the cosmos remains one of the greatest mysteries, one that extends beyond even the long arc of this galaxy's existence. For now, this stellar system remains an aberrant participant in the ongoing story of the cosmos. Its stars still shine, its nebulae still swirl with potential, and its future remains unwritten. Whether it eventually fades into isolation, merges with another galactic system, or becomes the cradle of new cosmic phenomena, it is a reminder that the universe is not static, it is an ever-changing expanse of creation, transformation, and mystery. The galaxy's journey, like the universe itself, is one of constant motion. And as long as observers exist to study it, to trace its evolution, and to uncover the forces that shape it, its story woven into the grand distance, a testament to the boundless nature of the cosmos. The passage of time within this galaxy, like that of all cosmic structures, is dictated by forces both seen and unseen. For now, it remains a place of energy and movement, a system still brimming with stellar activity in the subtle interplay of gravity, radiation, and magnetic fields. Yet the deeper laws of physics ensure that change is inevitable. The stars that shine today will one day burn out, their remnants drifting through space, forming the silent foundation of a future where darkness and cold dominate. Even in the near future, on a galactic scale, this system will begin to noticeable shifts. The rate of new star formation as available gas reservoirs dwindle, and stellar winds, supernovae, and active galactic feedback continue to expel material into intergalactic space. The most massive stars, those that once defined the brilliance of the galaxy's spiral arms, will be the first to vanish, leaving behind a less dynamic but still evolving stellar population. As the era of new stars comes to a close, the dominant sources of energy within the galaxy will change. While today it is driven by the nuclear fusion of young, luminous stars, in the future, much of its energy will come from compact remnants, white dwarfs, neutron stars, and black holes. These objects, relics of past stellar generations, will continue to interact in gravitationally complex ways, forming dense stellar clusters where unusual astrophysical phenomena may emerge. With no new material to sustain star formation, the galaxy will enter a state of slow structural decay. The spiral arms, once teeming with brilliant clusters of hot, young stars, will become more diffuse and less distinct. The central regions, dominated by older stars, will gradually take on a more elliptical shape, as stellar orbits become increasingly randomized due to long-term gravitational interactions. If the system experiences another it may retain much of its spiral character for an extended period, but eventually, it will lose the energy that sustains its grand structure. The presence of dark matter, though invisible, will continue to shape the motion of stars and stellar remnants. This unseen mass, concentrated in a vast halo extending far beyond the visible edges of the galaxy, will ensure that its overall gravitational integrity remains intact, even as individual stars come and go. Yet as time, the exact nature of dark matter's influence remains uncertain. If itself or decay's over timescales alter the galaxy's evolution in ways not yet fully understood. Far in the future, black holes will become the dominant gravitational players within the system. The central supermassive black hole, now a relatively quiet presence, may awaken if a galactic collision with new material to consume. However, if no such event occurs, it will continue to exist in dormancy, exerting its pull on stars and stellar corpses that orbit its dark center. Meanwhile, smaller black holes, formed from the collapse of once massive stars, will roam the galaxy, occasionally merging and releasing bursts of gravitation ripple through the fabric of space-time. The next phase in the galaxy's life will be white behind by sun-like stars will take trillions of years to cool to black dwarfs, their faint infrared glow into total darkness. The neutron stars, though more stable, will also lose energy over immense timescales, their once become featureless. In the most distant future, when even these last stellar remnants have faded, the galaxy will be reduced to a vast, dark cloud of compact objects. White dwarfs will have long since cooled beyond detectability. Neutron stars will have settled into silent motion, and the remaining black holes will be the only significant sources of gravitational influence. The occasional gravitational interactions between these objects may move them into intergalactic space, while others may sail inward toward the supermassive black hole at the center. Even black holes are not eternal. If the radiation hold true, over an unimaginable number of years, they will slowly evaporate, emitting minuscule amounts of radiation until they finally vanish. Final stages, the last remaining structures of the galaxy will disappear entirely, leaving nothing but the expanding void. Yet even in this apparent finality, the larger fate of the universe remains unknown. Some cosmological theories suggest that new physics could emerge at extreme timescales, allowing for the rebirth of matter, the formation of new energy structures, or even the possibility of an entirely new phase of existence. Other models, the universe expanding indefinitely, growing colder and more desolate as entropy reaches its maximum. But for now, this galaxy is still very much alive. It is a place where stars are born and die, where black holes lurk in the shadows, and where gas clouds drift between the stars, waiting to be pulled together into new systems. It is still undergoing change, still writing its story in the language of light and gravity. And as long as there are eyes to observe it, whether human or some other intelligence that may one day rise within its countless stars, its journey through time will remain an inspiration. It is a reminder that the universe is not a static void but an evolving, dynamic entity, filled with forces beyond our comprehension, shaping worlds beyond our reach. This galaxy's tale is far from over. It is but one greater cosmic narrative, one that stretches across the depths of space and the boundless of time. And as long as the universe itself exists, the echoes of its existence, its transformations, and its mysteries will endure, woven into the grand and infinite fabric of the cosmos. The journey of this galaxy is a testament to the changing nature of the cosmos, where time, gravity, and energy weave an unbroken transformation. Even as it moves toward a quieter, less dynamic state, the fundamental forces that shaped it continue to operate, ensuring that its evolution, though gradual, will never truly cease. As the last great bursts of star formation fade, the galaxy will settle into a state of equilibrium, where the remaining stars age and cool without the replenishment of new stellar generations. The once vibrant young blue giants and glowing nebulae will be replaced by an increasing dominance of red and orange stars, burn their fuel slowly and persist long after the more massive stars have perished. Over time, even the dwarfs appear, leaving behind a sky populated mostly by stellar remnants, silent echoes of a once thriving system. Though large-scale star formation will have ceased, cosmic interactions will continue on smaller scales. Gravitational encounters between stellar remnants may lead to occasional mergers, where white dwarfs collide to produce faint, short-lived bursts of energy. Some neutron stars in decaying orbits around one another may spiral inward over the course of eons, unleashing powerful gravitational waves in their final moments before merging into a single, ultra-dense object. These events, though rare, will be among the last luminous displays in the galaxy's history, marking the remnants of processes that once fueled its brilliance. At the heart of the system, the supermassive will remain the most dominant force, exerting its influence over whatever matter still orbits its deep gravitational well. If no new gas is available for accretion, it will exist in a solitude, an immense but invisible presence, the flow of material at the core. However, should future interactions send new objects toward it, whether wandering stars, souls, or the remnants of galactic mergers, still flare to life in brief, final outbursts of radiation before returning to dormancy. Beyond the slow transformation of the galaxy itself, the broader cosmic landscape will undergo a profound shift. The expansion of the universe, driven by dark energy, continues stretching the fabric of space, increases between galaxies. If current models hold true, this system will one day be so far removed from its nearest neighbors that no light from them will ever reach it again. It will exist in solitude, drifting in an ever-expanding void, separated from any potential sources of new energy or interaction. In the distant future, even the most enduring stars will fade, which burn their hydrogen reserves with remarkable efficiency, will eventually deplete their fuel, transitioning into dim white dwarfs, scattered throughout the galaxy, will continue their slow cooling process, radiating away their last traces of heat until they become black dwarfs, invisible and undetectable, existing only as faint gravitational imprints in the darkness. The galaxy, once a brilliant collection of spiraling stars and nebulae, will become a quiet graveyard of matter, a system of dead stars, black holes, and unseen remnants, orbiting in patterns set long ago changing. The gravitational pull that once held it together will remain, but without active energy sources, it will simply persist as a vast structure of cold, inactive objects, bound by forces that no longer shape new formations. But even these lingering remnants will not endure forever. If Hawking radiation is correct, then over unimaginable spans of time, even the black holes that dominate the galaxy's final phase will slowly evaporate, radiating away their mass particle by particle until nothing remains. The last trace of structure within this system, indeed, within any system, will be erased as even these cosmic titans fade into nothingness. At this stage, the universe itself may have reached what is theorized as the heat death, a state where entropy has maximized, all available energy has been evenly distributed, and no further work can be done. The last remaining particles will drift aimlessly in a sea of darkness, with no stars to shine, no forces to bind them together, and no structure left to shape the cosmos. And yet, even in this seemingly final state, mysteries remain. Some theories propose that at extremes, new physics may emerge, allowing for the spontaneous formation of quantum fluctuations that could give rise to entirely new structures, perhaps even a new universe. Others suggest that unknown forces, current understanding, could initiate a cosmic rebirth, resetting the universe into a new cycle of expansion, contraction, and formation. For now, however, this galaxy remains a place of light, energy, and motion. It is still home to the stars, to planetary, and to forces that shape the cosmos on scales both vast and It is still evolving, still existing as part of the grand, ever-unfold of the universe. And as long as there are it, whether human or some future intelligence that may one day in its stars, its journey will not be forgotten. It will stand as a testament to the vastness of time, the relentless power of cosmic and the mystery of existence itself. Even in the face of inevitable entropy, depths of the farthest future, the legacy, its cycles of formation, its silent end, will into the fabric of the cosmos, a whisper in the endless space and time. As the inevitable march of entropy dictates the distant fate of this galaxy, its existence, past, present, and future, remains a crucial part of the larger cosmic narrative. While its stars will one day fade, while its spiral arms will dissolve into a formless collection of stellar remnants, and while even its black holes will eventually disappear, it is not a mere passive participant in this grand story. Every collision, every burst of star formation, every gravitational action it has ever undergone has contributed to shaping the vast, evolving tapestry of the universe itself. For now, it is still a place of motion, where stars drift along their ancient orbits, where remnants of once massive suns cool in the silence of space, and where the invisible forces of dark matter still hold it together. The fabric of space-time bends subtly around its remaining black holes, the gravitational wells marking where brilliant clusters of stars once illuminated the cosmic night. Even as star formation ceases, interactions between stellar remnants will continue. White dwarfs may occasionally merge, final supernovae that momentarily rekindle lost over eons. Some neutron stars may collide, in bursts of gamma radiation that flash across space before vanishing into the abyss. These events will become rarer and rarer as time stretches forward, their light appearing like distant echoes of an era that once flourished. If a cosmic traveler, a future intelligence from a civilization born on one of this galaxy's planets, were to witness its slow transformation, they would see it as a system settling into a quiet, eternal slumber. The intricate balance of forces that once gave rise to its grand structure will dissolve, leaving behind a ghost of what once was. The beautiful, swirling motion of its spiral arms will be nothing but a memory written in the positions of long-cooled stellar remnants, their orbits preserving the shape of the past long after the light has faded. And yet, even in this state of near total stillness, the galaxy will continue to move. It will drift through the expanding universe, carrying with it the remnants of countless millions of stars, planets, and possibly even life that once arose in its systems. Every star that has ever shone, ever formed, every cosmic event that has ever unfolded within its boundaries has left a mark upon the larger fabric of reality. But what lies beyond the end? Some theories suggest that as the expansion of the universe, structures like this galaxy will become increasingly isolated, eventually disappearing beyond the event horizons of one another. This would mean that, in the deepest future, nothing from the outside universe would be able to reach this lone stellar graveyard. It would be complete solitude, no longer connected to the broader cosmic web from which it once drew its material and energy. Yet other possibilities remain open. There are theories that hint at the idea of cosmic rebirth, suggesting that fundamental forces may shift over unimaginable timescales, triggering a new phase of universal evolution. Perhaps the very fabric of space-time will undergo a transformation, giving rise to new structures, new energies, or even new forms of matter. Could something rise from the ashes of this long silent galaxy, reshaping its cold remnants into their universe? Or perhaps, if there is intelligence capable of enduring across such timescales, this galaxy may not remain a passive relic of the past but instead a domain of cosmic engineering. If civilizations survive the death of their stars, could they find ways to reignite new suns? Could they harness the gravitational energy of black holes to create new sources of warmth and light? Could they defy the seemingly inevitable fate of entropy, bending the rules of nature to construct a new age of stellar activity? For now, such questions remain beyond our reach. What is certain, however, is that the universe is not a static entity, nor has it ever been. From the moment of its birth, it has been in constant flux, each stage leading into the next, each transition reshaping the fate of galaxies, stars, worlds. This galaxy's story, though it may seem to end in silence, is not a tragedy. It is a story of cycles, transformations, and endurance. It is a reminder that even in the face of entropy, in the face of an ever-expanding cosmos, there is meaning in the motions of celestial bodies, in the interactions of cosmic forces, in the rise and fall of stellar systems. It is not just a fading structure in an ancient universe, it is a link in a chain that stretches from the distant past into the unknowable future. It is a testament to the grand forces that govern reality, a cosmos will resonate across time. And as long as there are observers, whether human or otherwise, to look toward the stars, to marvel at the scale of existence, then the galaxy will never truly be over. It will live on in the minds that remember it, in the equations that describe, and in the unbroken universe itself, a whisper in the voice in the infinite, a mark upon. Even in the farthest reaches of time, when the last embers of this galaxy have faded and its structure has dissolved into the silent drift of stellar remnants, its existence will remain woven into the universe. The forces that shaped it, the stars that once illuminated its spiral arms, and the events that unfolded within its vast expanse have upon reality itself. Though no longer a place of brilliant star clusters and luminous nebulae, will not be forgotten by the cosmos. The energy that once flowed through its stars has been dispersed, the elements forged in their nuclear furnaces scattered across the void, now part of an unseen legacy stretching far beyond its borders. The gravitational ripples from ancient collisions still echo through spacetime, faint but real, inscribed into the very structure of the universe. In a universe where time stretches infinitely forward, the galaxy's past is not erased but absorbed into the grand continuity of existence. Every burst of stellar radiation, every gravitational interaction, every moment of transformation has contributed to shaping the cosmos as it is now, and as it will be in the future. Yet if the universe itself has an ultimate fate, if the expansion continues to accelerate, or if new physics emerges beyond our understanding, then even the idea of permanence may be an illusion. If dark energy persists, this galaxy will be carried ever outward, away from all others, lost in a cold and empty expanse where no new interactions can take place. Future, its remnants will continue their endless drift, untouched, unseen, unknowable to anything that might still exist elsewhere. But if the universe is cyclic, if there is a deeper pattern beyond the present expansion, then perhaps this is not the truth. Some theories suggest that the cosmos may one day contract, reversing its expansion and pulling everything back toward a new singularity, a rebirth where all past matter and energy are reshaped into the foundation of a new reality. If such a fate awaits, then this galaxy, though long dissolved, may become part of the material that fuels the birth of new stars, new galaxies, new structures beyond imagining. And even if the cosmos remains in perpetual expansion, with entropy driving it toward darkness, there may yet be unseen forces at play. Perhaps deep in the void, unknown mechanisms could reignite cosmic processes, birthing new structures in ways we cannot yet comprehend. Could remnants of this galaxy, scattered and cold, find new purpose in an epoch where the laws of physics themselves change? If intelligence endures, if civilizations, whether from this galaxy or another, find ways to persist beyond the deaths of their stars, then the knowledge of what once was will not vanish. Records of this galaxy's past may be preserved, its structure mapped, its evolution studied by minds that have transcended ordinary limitation entropy. The image of its grand spiral form, long since unraveled, may still exist in archives that survive beyond stars, beyond black holes, beyond even the last remnants of ordinary matter. For now, this galaxy still turns, still shines, still plays its role in the vast cosmic dance. Its stars are not yet gone, its remnants not yet scattered to the cold depths of time. And as long as it exists, as long as light still escapes from its distant reaches, its presence in the universe remains undeniable. And even when its last light has faded, when its black holes have evaporated, when every particle has drifted into the background radiation of a silent cosmos, its existence will not have been in vain. It has been a part of something far greater, a universe where time does not erase but instead transforms, where energy does not disappear but shifts into new forms, where every celestial body, no matter how fleeting in the grand eternity, contributes to the larger unfolding of reality. This galaxy's story may end in darkness, but it does not end in nothingness. It remains, always, a chapter in the infinite book of the cosmos, its essence forever imprinted upon the grand and unending tapestry of space and time. Even in the depths of an aging universe, slowly claims what once shone. The essence of this galaxy endures. It may fade, its structures may dissolve, and its energy may disperse into the vastness of space, but its influence, its mark upon the cosmic stage, remains. Every atom, every photon, every gravitational wave that ever emanated from this system is now part of something greater. The elements forged in its stellar cores have traveled far beyond its borders, carried by supernovae, stellar wind, galactic currents to become part of new worlds, new structures, perhaps even new life. Its own light may no longer shine, the echoes of its existence persist in ways beyond our current comprehension. If there are still observers, beings capable of witnessing the slow unraveling of the cosmos, they may look upon this galaxy not as a relic, but as a monument to the vast interplay of forces that have governed the universe since its birth. To them, it may serve as a record of everything that has come before, a cosmic archive written not in books but in the arrangement of dead stars, in the subtle distortions of space-time left by its long-past inhabitants. Perhaps, in the farthest reaches of time, it will endure, outlasting even the stars themselves. If such minds exist, they may develop ways to resist the pull of entropy, to construct new energies of a dying universe. Perhaps they will find remnants of galaxies like this one, gathering their scattered pieces to forge something new in a universe that no longer creates but owns. Even if no civilization survives, if no mind remains to fundamental laws of physics dictate that nothing is ever truly lost. Energy changes form, matter disperses, structures dissolve, but the sum total of all that has ever existed continues to shape. This galaxy, even in its final silence, is part of folding, scattered among the gravity still shaping the motion of celestial bodies long after its own light has faded. It does not forget, not in the way living beings do. The fabric of spacetime itself carries the imprints of everything that has ever been, the traces of every interaction, every force, every transformation. This galaxy, now only a whisper in the void, is woven into that vast, eternal record. And so, its journey does not truly end. It is not mere that unending expanse of time, but a contributor to something far greater. Whether the universe cycles anew, whether unknown forces bring about a rebirth, or whether entropy carries everything toward a quiet and endless expansion, this galaxy will always live. It will always have been part of the cosmic story. Its legacy is written in the light that once traveled across the stars, in the gravitational ripples it sent across space, in the elements it forged that now drift unseen among the ruins of a fading cosmos. It is a memory inscribed upon the infinite, a presence that will never vanish. And as long as there are minds, whether now, in the distant future, or in some unknown epoch of reality, to look out into the dark and wonder, then its story, like the universe itself, will never truly be over. Even in the silent vastness of a universe approaching its final, unknowable fate, the existence of this galaxy remains an indelible part of the cosmic record. Though its stars have long since faded, their energy spent, their structures dissolved into the cold drift of intergalactic dust, the very fact that they once shone, that they once gave form to a grand and spiraling structure in the void, ensures that their influence is never truly erased. For now, the universe still expands, still carries the remnants of galaxies like this one outward into the growing abyss. If cosmic acceleration continues unchecked, then the final state of all things may be one of endless separation, an era where the last remaining fragments of matter are so distant from one another that no new structures can form, where even the faintest echoes of past galaxies are stretched across a universe that has grown too vast, too cold, too empty for anything to emerge anew. But even in such a fate, even in a universe toward silence, the memory of this galaxy remains inscribed in the very time. Every wave it ever generated, every it once released, every particle it's a cosmos is now a part of something larger, a universe that has, for all its vastness, been shaped by each of its stars, each of its forces, each of its countless interactions. Perhaps, beyond even the longest timescales we can fathom, something new will arise be an ending. Some theories suggest that the very structure of space itself may one day fluctuate to new cosmic conditions. Energy of long-faded galaxies will one day serve as the seeds of something yet to be born. Could the remnants of matter, scattered across the vast, darkening cosmos, blocks of a new age of light and structure? And if intelligence endures, if there are minds capable of witnessing the slow transformation of the universe into something beyond what we now understand, then they, too, may play a role in ensuring that this galaxy's legacy is not forgotten. Whether through archives stored beyond the limits of time, or through vast cosmic engineering projects that seek to resist entropy itself, there may still be those who hold the knowledge of what came before, who remember the age of galaxies, of stars, of motion and energy. Even if all else fades, even if no one remains to remember, this galaxy's story will have mattered. It was part of the great unfolding of the cosmos, part of the immense and intricate symphony of forces that brought structure from chaos, light from darkness, form from formlessness. It existed, and that alone is enough to secure its place in the eternal record of all that has ever been. For now, its journey continues, its last remnants still drifting, still bound by the gravitational echoes of what it once was. And as long as the universe exists in any form, whether expanding into infinity, collapsing into rebirth, or transforming into something we cannot yet comprehend, this galaxy, and ever belong to it, will remain a part of the great and endless story of the cosmos. Even in the deep future, when the last remnants of matter drift in a universe grown vast beyond measure, the essence of this galaxy remains woven into the silent fabric of existence. Though no longer a luminous spiral of stars, though its structures have dissolved into the slow tide of entropy, it was, and therefore it is. Its light once traveled across cosmic distances, its gravity once shaped the orbits of countless worlds, and once played their part in the grand symphony of the cosmos. The universe itself is a memory, written not in ink but in the motion of celestial bodies, in the invisible distortion left by the passage of stars, in the delicate balance of energy and void. This galaxy, long past its era of brilliance, has left its mark in ways that cannot be undone. The atoms forged in its core, scattered by billions of years ago, may still drift through space, waiting for a new gravitational well to gather them, to shape them into something yet to be. Perhaps no such rebirth will come. If the universe continues its expansion without bound, if no new structures can form, then matter itself may thin into nothingness, stretched by the relentless pull of dark energy. In such a future, the very idea of a galaxy, of stars and planets, will belong to a past so distant that it can no longer be reconstructed. The distances between remnants will grow so great that no interaction will ever occur again, no light will ever reach another point, no motion will ever again alter the stillness. And yet, even then, the trace of what once was will not be truly lost. The information of this galaxy's existence, of the energy it once radiated, of the forces it once exerted, will remain encoded in the quantum state of reality itself. Some physicists theorize that no information is ever truly that even when stars collapse, when matter disintegrates, when black holes evaporate, the fundamental data of their existence persists in some unknown, hidden form. If this is true, then this galaxy, though long gone, will never have been erased. Perhaps, beyond the horizon of time, something will arise to read the final traces of what has been. Perhaps an intelligence beyond, existing in a far future state where entropy has slowed, where the last pockets of energy are gathered and used with impossible precision, will find a way to reconstruct the past. Long-dead galaxies will be retrieved back in ways we cannot yet conceive, allowing some distant observer to witness the spiral arms, to see the stars as they were, to trace the paths of planets that no longer exist. And even if no mind survives to witness it, even if intelligence fades along with the last, the fact remains that it was. This galaxy existed, it played its role in the cosmic ballet. It was part of something immense, something unknowable. That alone secures its place in the infinite continuum of reality. The universe is vast beyond understanding, and time stretches forward into the unknowable. Yet within that, every star that has ever, every world that has ever formed, every force that has ever acted upon matter to the larger unfolding of all that is. This galaxy, though now a ghost among the stars, was part of that story. It remains part of that story. And as long as the cosmos endures, its place in that endless, evolving narrative will never be undone. Even in the farthest reaches of eternity, where time itself stretches into the unknowable, the echoes of this galaxy persist. Though its stars have long since faded, though its structure has unraveled into the slow drift of forgotten remnants, it remains inscribed in the very essence of the cosmos. No moment, no force, no celestial motion is ever truly erased. All that has ever been continues to exist in the grand unfolding of reality, woven into the invisible fabric that binds all things together. The final remnants of this galaxy, white dwarfs long turned to black dwarfs, neutron stars reduced to frozen cores of dense matter, and black holes evaporating into the void, will persist until the very last motions of the cosmos come to a halt. If the universe continues to expand indefinitely, these fragments will drift apart, growing more isolated until they are separated by such great distances that even the fundamental forces of nature will no longer bind them together. Each will become a solitary traveler in an ever-moving through a cosmos where no new stars will ever ignite, where no light will ever again break the silence. Yet even in such an ending, the memory of this galaxy is not truly lost. If the nature of information is such that it cannot be destroyed, then every event that has unfolded here, every supernova that once ignited, every world that once formed, every star that once shone, still exists in some unfathomable way. The universe itself, as it once was, may be recoverable, it's put in ways beyond our current comprehension. Perhaps there will come a time, billions upon billions of years from now, when something, or someone, reaches into the deep archives of space-time and resurrects the lost light of this galaxy, reconstructing its stars, its planets, its structure from the echoes it has left behind. But even if no such recovery is possible, even if all knowledge is lost to entropy, the fact remains that it was. This galaxy existed. It was part of something vast, something beautiful, something impossible to fully grasp. It was a beacon in the spiral of fire, a place where matter danced in luminous patterns for a brief moment in the infinite. That moment may have passed, but its impact remains, woven into the grand design of the universe, forever a part of the great and infinite tapestry of existence. And so, as long as the cosmos endures, even in the cold and silent twilight of time's final stretch, the presence of this galaxy will never truly vanish. It will remain, an echo in the void, a whisper across eternity, a mark upon the unbroken continuum of all that has ever been. And so, as the universe drifts ever forward into the unknown, this galaxy's journey, though long past its most luminous days, remains part of the grand, unfolding story of the cosmos. It was a place of brilliance, where stars were born, where worlds may have formed, where forces beyond comprehension wove together light and matter into a vast and intricate dance. Though time has carried it towards stillness, though its stars have long since burned their last, its presence is not forgotten, it is etched into the very fabric of existence. For even when the last light has faded, even when the final remnants of matter dissolve into the expanding void, what was will always have been. This galaxy of things played its part in the shaping of the cosmos, and that role, whether small or immense, cannot be undone. It is a whisper across the infinite, a moment of structure in an endless sea of transformation, a brief flicker of ordered motion before the quiet embrace of eternity. And though no mind may remain to remember, though no eye may look upon its spiraling form and marvel at its beauty, its essence will always be woven into the cosmic whole. Lost, nor meaningless, it is simply one chapter in the unending book of the universe, a chapter that will forever exist within the vast and unknowable expanse of time. For the universe is not static, nor is it finite in what it holds. As long as existence itself endures, as long as there is space and time in which new things may arise, nothing is ever truly gone. This galaxy's light may have faded, its matter may have scattered, its structure may have dissolved into the cosmic night, but it was, and that is enough. It remains, in echoes, written into the physics of spacetime, in the particles that once formed its stars, now futures yet. And as long as the universe itself persists, its story, like all stories written in the cosmos, will never truly end. The term Eye of God is often associated with celestial phenomena, most notably the Helix Nebula, NGC 7293. This planetary nebula, located approximately 650 light-years from Earth in the constellation Aquarius, has captivated astronomers public alike due to its striking resemblance to a human eye. However, beyond appeal, the Helix Nebula serves as a crucial subject for scientific investigation, offering insights into the life cycle of stars and the dynamics of interstellar matter. This nebula represents the final stages of a sun-like star's evolution. When a star exhausts its nuclear fuel, it expands into a red giant before shedding its outer layers, forming a luminous cloud of ionized gas. The central remnant, a white dwarf, emits ultraviolet radiation, causing the ejected material to glow. The result is a stunning display of concentric shells of gas, rich in hydrogen, oxygen, and nitrogen. The intricate structure of the nebula, shaped by stellar winds and radiation pressure, reveals the complex interplay between a dying star and its surrounding environment. Observations of this so-called cosmic eye have been instrumental in advancing our understanding of stellar death. Imaging from telescopes like the Spitzer Space Telescope has allowed astronomers to analyze the composition of the nebula, detecting molecules such as carbon dioxide and silicates, essential building blocks for planetary formation. Meanwhile, the Hubble Space Telescope's high-resolution images have provided a detailed view of its intricate filaments and knots of gas, remnants of the star's outer layers interacting with the interstellar medium. The celestial iris is also a valuable laboratory for studying the transition of matter from stars back into the cosmos. As the nebula disperses over thousands of years, the elements it contains will eventually contribute to the formation of new stars, planets, and potentially even life-bearing worlds. This cyclical nature of stellar material underscores the interconnectedness of cosmic evolution. Beyond the Helix Nebula, other nebulae resembling an astral pupil in the universe, each offering unique insights into astrophysical processes. The Cat's Eye Nebula, NGC 6543, in the constellation Draco, for example, displays a highly complex structure, with multiple shells and a turbulent interior shaped by a binary star system. These observations suggest that planetary nebulae, despite their name, are far more intricate than early astronomers had assumed. From a broader perspective, the study of universal ocular structures is vital for understanding the fate of our own Sun. In approximately billion years, our star will undergo a similar transformation, shedding its outer layers and leaving behind a dense white dwarf. By nebulae like the helix, astronomers can predict how this process will unfold, offering a glimpse into the distant future of our solar system. Furthermore, the galactic lens concept extends beyond optical astronomy. Radio and X-ray telescopes have detected from planetary nebulae, revealing energetic interstellar remnants and their environments. These multi-wavelength observations help scientists piece together the puzzle of stellar evolution, uncovering processes that shape both microscopic and cosmic scales. The fascination with the heavenly gaze is national astronomy. Public interest in these formations has been fueled by their striking imagery, often featured in popular science publications and space agency releases. The Helix Nebula, in particular, has been dubbed the Eye of God in mystic interpretations, symbolizing the vastness and mystery of the cosmos. As technology advances, new observational methods will allow scientists to further probe the depths of these stellar eyes. Upcoming space missions, such as the James Webb Space Telescope, promise to uncover structures, shedding light on the physics of dying stars and their role in the cosmic cycle. By continuing to explore these celestial formations, we not only deepen our understanding of astrophysics but also reinforce humanity's connection to the universe. The ethereal vision, as seen in nebulae resembling a celestial eye, represents the aesthetic verse to profound astrophysical insights. As observational techniques evolve, astronomers continue to complexities hidden within these cosmic structures, shedding light on the processes governing stellar evolution, interstellar chemistry, and the intricate balance between destruction and creation in the universe. One of the most interesting of the spectral gaze is the role planetary nebulae play in the chemical enrichment of the cosmos. Stars function as nuclear forges, synthesizing elements through fusion reactions over millions or billions of years. However, the true dissemination of these elements occurs during the final stages of a star's life. The Helix Nebula, like other similar structures, is rich in heavy elements such as carbon, oxygen, and nitrogen, materials that will eventually be incorporated into new generations of stars and planetary systems. Without this process, the fundamental building blocks of life would not exist, reinforcing the notion that planetary nebulae serve as crucial links in the cosmic cycle of matter. Recent observations using spectroscopic analysis have provided deeper insight into the composition of the celestial observer. By analyzing the emitted light at different wavelengths, have identified complex molecules and dust grains within these nebulae. The presence of polycyclic aromatic hydrocarbons, PAHs, organic molecules that form in the cooling gas of planetary nebulae, suggests that such regions may contribute to the organic inventory of the interstellar medium. This discovery has significant implications for astrobiology, as it indicates that the ingredients for life may be widely distributed throughout the universe, seeded by dying stars. Beyond their chemical contributions, the cosmic sentinel structures offer a glimpse into the physics of stellar winds and radiation-driven dynamics. The shaping of planetary nebulae is influenced by multiple factors, including the stellar wind from the progenitor star, magnetic fields, and even potential interactions with unseen companion stars. High-resolution imagery has revealed asymmetric structures, suggesting that many of these nebulae are not formed in isolation but are instead sculpted by gravitational interactions and external forces. For example, observations of the Galactic Observer using radio telescopes have unveiled the presence of collimated outflows, narrow, high-velocity streams of gas extending from the central star. These outflows, sometimes appearing as jets or bipolar lobes, provide evidence that the central white dwarf may have undergone interactions with an unseen companion, influencing the final distribution of expelled material. Such findings challenge earlier models that depicted planetary nebulae as simple, spherical shells and instead reveal a far more dynamic and chaotic process. Furthermore, the astronomical eye plays a role in the broader galactic ecosystem. The material ejected from these nebulae does not simply dissipate into the void, instead, it enriches surrounding molecular clouds, regions where new stars are born. This continuous recycling of stellar material ensures that each star contains heavier elements than the previous, gradually shaping the chemical composition of galaxies over cosmic timescales. The study of these structures is poised for a major leap forward with the deployment of next-generation telescopes. The James Webb Space Telescope, JWST, with its unprecedented infrared capabilities, is expected to provide an even clearer view of the spectral lens, allowing astronomers to peer deeper into the dust-rich regions of planetary nebulae. By analyzing the thermal emissions from dust grains, scientists will gain insight into the temperature distribution and physical properties of nebular material, further refining our understanding of the late stages of stellar evolution. Beyond space telescopes, advances in computational astrophysics have allowed researchers to simulate the formation and evolution of the celestial portal. These simulations, incorporating fluid dynamics, radiation transport, and magnetic fields, are providing new models for how planetary nebulae develop over time. Some of the latest findings suggest that many of the intricate patterns observed in nebulae, such as filaments, arcs, and knots, are the result of instabilities in the stellar wind rather than external influences alone. Understanding these processes is essential not only for nebular studies but also for refining models of star formation and galaxy evolution. The enduring fascination with the universal aperture extends beyond professional astronomy. Throughout history, various cultures have interpreted celestial formations as divine symbols, and the appearance of an eye-like structure in space has only strengthened such associations. The Helix Nebula, in particular, has been widely featured in discussions about cosmic symbolism, often viewed as a metaphor for the universe observing itself. While such interpretations lie outside the realm of scientific inquiry, they highlight the profound psychological impact that astronomical imagery can have on human thought. As we continue to refine our observational tools and theoretical models, the heavenly sentinel remains a focal point of discovery. With each new dataset, astronomers are piecing together stellar depth, intricate individual stars, and the vast cosmic web they help to shape. The more we study these celestial phenomena, the clearer it becomes that the universe is not a static entity but a living, evolving system, one where each dying star to the worlds. The Imperial Observer is not just a spectacle to behold but a scientific treasure trove, holding secrets that continue to push the boundaries of human knowledge. Whether through advanced spectroscopy, deep space imaging, or theoretical simulations, each new discovery brings us closer to understanding the mechanisms that govern the cosmos and our own place within it. The cosmic observer, embodied in nebulae such as the helix, remains an essential understanding the interstellar birth, life, and demise. Each observation refines our grasp of the physical mechanisms that shape these celestial formations, providing new insights into the fate of stars, the dispersion of elements, and the ever-changing nature of the universe itself. One of the most compelling aspects of the astronomical aperture is its role in tracing the thermal and kinetic properties of gas expelled from dying stars. Observations across multiple wavelengths, from visible light to X-rays, have revealed that the temperatures within these nebulae can vary dramatically. The outer regions, composed of cooler gas, glow primarily in optical wavelengths, while the inner core, heated by the residual emits in the ultra-ray spectrum. This complex temperature gradient is a product of radiation interactions, with high-energy photons ionizing the surrounding material and gradually dissipating into space. Through high-resolution spectroscopy, researchers have uncovered that the stellar distinct velocity patterns, suggesting that the ejection of material is not uniform but rather occurs in pulses or waves. These periodic outflows likely result from fluctuations in the dying star's energy output, causing it to expel shells of gas at different rates over thousands of years. By studying the rates, astronomers estimate the age of planetary nebulae, offering a timeline for their formation and eventual dissipation. The Galactic Watcher is also central to the study of interstellar dust formation. As stars shed their outer layers, they release not only ionized gases but also microscopic solid particles, including silicates, carbonaceous grains, and even crystalline structures. These dust grains, once released into space, can act as seeds for future planetary systems. Studies of nebulae resembling the celestial portal have shown that these dust particles can survive for extended periods, eventually merging with molecular clouds where new stars and planets emerge. Understanding how these dust grains form, evolve, and disperse is crucial for unraveling the origins of complex planetary environments. Recent investigations using radio telescopes have revealed intriguing details about the magnetic fields within the universal lens. Magnetic interactions play a critical role in shaping the flow of ejected material, influencing the symmetry, or asymmetry, of planetary nebulae. Some of the most striking examples of these effects can be seen in nebulae with pronounced bipolar lobes, where charged particles are channeled along magnetic field lines, creating hourglass-shaped structures rather than simple spherical shells. The presence of such magnetic effects suggests that dying stars may possess previously undetected magnetic activity, adding another layer of complexity to our understanding of stellar evolution. The ethereal gatekeeper is not merely a relic of stellar death but a dynamic entity, continuously evolving as it expands into interstellar space. Observations indicate that as planetary nebulae disperse, they interact with their surroundings, sometimes triggering new star formation in nearby regions. Shock waves from these nebulae compress interstellar gas, creating dense pockets where gravity can take hold, potentially leading to the birth of new stars. This process, known as triggered star formation, highlights the interconnected nature of cosmic structures, where even the end of a star's life contributes to the genesis of another. Looking toward the future, next-generation astronomical instruments will further refine our understanding of the spectral sentinel. Ground-based observatories equipped with adaptive optics are already providing sharper views of nebular details, revealing previously unseen structures within these gaseous remnants. Space-based observatories, such as the James Webb Space Telescope, will allow astronomers to penetrate deeper into the obscured regions of planetary nebulae, uncovering the chemical and physical conditions within their dust clouds. Moreover, the study of the heavenly observer extends beyond individual nebulae to broader cosmic patterns. Comparing planetary nebulae across different galaxies has provided valuable insights into the chemical evolution of the universe. By analyzing the elemental abundances in distant nebulae, astronomers can trace how galaxies enrich themselves over time, revealing the gradual buildup of heavy elements essential for planet formation and, ultimately, life. The ongoing exploration of the celestial sentinel reinforces a profound truth: the universe is an ever-changing, interconnected system where every phase of stellar life contributes to the greater cosmic cycle. The dust and gas expelled by dying stars do not vanish into oblivion but instead become part of new cosmic structures, whether future planets, star-forming regions, or the diffuse interstellar medium that permeates galaxies. The continued study of these enigmatic formations is not just a quest for knowledge but also a reflection of humanity's deep-rooted curiosity about the cosmos. As we gaze upon these celestial eyes scattered throughout the universe, we are reminded that our own existence is intricately linked to the life cycles of the stars, that the atoms in our bodies were once forged in the hearts of ancient suns. Thus, the ethereal gaze remains both a scientific marvel and a cosmic symbol, a reminder that the universe itself is watching, evolving, and shaping the future in ways we are only beginning to comprehend. The celestial sentinel, as seen in the intricate formations of planetary nebulae, continues to serve as a window into the cosmic processes that govern the transformation of stars. Each observation adds new layers to our understanding of how these luminous remnants disperse their material, enriching the interstellar medium and influencing the next generation of celestial bodies. One of the most striking revelations about the cosmic watcher is the role of binary star systems in shaping nebular structures. While early models of planetary nebulae assumed a simple, spherical expansion of gas, modern high-resolution imagery has demonstrated that many of these formations exhibit asymmetric and highly complex shapes. Bipolar outflows, spiral patterns, and intricate filaments suggest the presence of secondary stellar companions that may interact gravitationally with the evolving nebula. These interactions lead to mass transfer, angular momentum redistribution, and the formation of dense equatorial rings or lobes of gas. Recent research into the galactic eye using data from the Atacama Large Millimeter/Submillimeter Array, ALMA, has provided unprecedented detail on the molecular composition of these nebulae. Scientists have detected not only simple molecules like carbon monoxide but also more complex organic compounds that suggest that nebular environments serve as chemical laboratories. These findings are crucial for understanding the origins of organic molecules in space, as planetary nebulae may act as dispersal points for the fundamental ingredients of life. Beyond their chemical complexity, the universal gaze nebulae also function as beacons of cosmic timekeeping. By measuring the expansion rates of different nebular shells, astronomers can determine how long a planetary nebula has been forming and predict how it will eventually fade into the interstellar medium. This timeline provides a framework for estimating the duration of different phases in stellar evolution, contributing to a broader understanding of how stars transition from red giants to white dwarfs. Additionally, X-ray observations of the spectral portal have revealed high-energy interactions occurring at the cores of some planetary nebulae. The remnant white dwarfs at the center of these formations often emit strong ultraviolet and X-ray radiation, which interacts with the surrounding gas to produce shock waves and ionized regions. These high-energy processes can influence the distribution of elements within the nebula, accelerating their dispersal and further enriching the surrounding galactic environment. The ethereal sentinel is not a static entity but rather a constantly evolving formation that continues to change even after the initial ejection of stellar material. Over time, the gas and dust within the nebula expand outward, gradually thinning as they mix with the surrounding interstellar medium. Eventually, after tens of thousands of years, the nebula will disperse completely, leaving behind only the white dwarf, a compact stellar remnant composed primarily of carbon and oxygen. However, the impact of the heavenly iris does not end with the fading of the nebula itself. The elements and molecules released by dying stars contribute directly to the formation of new stellar systems. Regions rich in planetary nebulae, such as the Orion arm of the Milky Way, contain some of the highest concentrations of interstellar dust and gas, making them prime sites for star formation. In this way, planetary nebulae act as catalysts for the next generation of cosmic evolution, ensuring that the cycle of stellar birth and death continues indefinitely. Future missions, such as the planned Extremely Large Telescope (ELT), and the next generation of space observatories, will provide even deeper insights into the structure of the astronomical eye. By using advanced spectrographs and adaptive optics, astronomers will be able to resolve individual knots of gas, trace their movements over time, and further refine models of how nebulae evolve under different conditions. The continued fascination with the stellar observer stems from both its scientific significance and its aesthetic grandeur. As one of the most visually striking phenomena in space, the Helix Nebula and its counterparts serve as reminders of the vast and intricate processes that shape the universe. They are not merely remnants of dying stars but active participants in the cosmic narrative, bridging the past and future of stellar evolution. In the grand scheme of the universe, the ethereal gateway stands as a testament to the interconnectedness of all cosmic phenomena. From the nuclear reactions within stars to the dispersal of elements across galaxies, planetary nebulae encapsulate the story of how matter cycles through the cosmos, influencing everything from the formation of planets to the potential emergence of life. As our observational capabilities expand and our theoretical models improve, the celestial guardian will continue to be a focal point of astronomical discovery. With each new revelation, we move one step closer to understanding not just the life cycle of stars, but the fundamental principles that govern the very fabric of the universe itself. The astral sentinel, embodied in planetary nebulae, represents a crucial phase in the grand cycle of stellar evolution. As researchers delve deeper into these enigmatic formations, they uncover new layers of complexity, revealing that the end of a star's life is not merely an endpoint but a transformative process that fuels the universe's ongoing dynamism. One of the most intriguing aspects of the Cosmic Guardian is its connection to white dwarf formation. The central star of a planetary nebula, having exhausted its nuclear fuel, contracts into a dense, hot core that will eventually stabilize as a white dwarf. These remnants, though small in size, typically no larger than Earth, contain the majority of the original star's mass, making them incredibly dense. Over billions of years, they will cool and fade, but their existence provides a glimpse into the fate of our own Sunday. Studying these objects allows astronomers to predict how similar stars, including our own, will evolve in the distant future. Furthermore, the galactic sentinel plays a crucial role in regulating the composition of the interstellar medium. The gas and dust expelled by dying stars contain elements such as carbon, oxygen, and nitrogen, key ingredients for planetary formation. Without planetary nebulae dispersing these enriched materials, future generations of stars and planets would lack the necessary heavy elements to form rocky worlds, atmospheres, and potentially life. In essence, every terrestrial planet, including Earth, owes its existence to the contributions of ancient nebulae that came before. Recent advancements in radio and millimeter wave astronomy have provided new insights into the molecular processes occurring within the celestial guardian. Observations using the ALMA telescope have revealed the presence of molecular outflows that extend far beyond the visible boundaries of these nebulae. These outflows, composed of complex hydrocarbons and dust grains, suggest that planetary nebulae are not merely dispersing material into space but actively contributing to the chemical evolution of their host galaxies. Another critical discovery regarding the spectral watcher is the presence of highly structured ionization fronts within many nebulae. These ionization fronts occur when the intense radiation from the central white dwarf collides with the surrounding gas, creating sharp boundaries between ionized and neutral regions. These structures can appear as intricate filaments, knots, or even comet-like tails pointing away from the central star. The discovery of these fine details challenges previous models that assumed a more uniform expansion of planetary nebulae, indicating that localized instabilities and turbulence play a significant role in shaping these formations. In some cases, the heavenly vision has been found to exhibit signs of past violent interactions, possibly with unseen stellar companions. Certain planetary nebulae, such as the Necklace Nebula, display ring-like structures that suggest they were shaped by binary star interactions. When a dying star has a close companion, it can lead to complex mass exchange processes that produce symmetrical or spiral formations within the nebular shell. The presence of these structures suggests that planetary nebulae may serve as tracers for binary evolution, helping astronomers study the influence of stellar companions in shaping the final stages of stellar life. Looking ahead, the next generation of space telescopes promises to unlock even deeper secrets of the universal sentinel. The Nancy Grace Roman Space Telescope, set to launch in the coming decade, will provide wide-field surveys of nebular environments, allowing scientists to catalog planetary nebulae across vast regions of the Milky Way. Meanwhile, advancements in gravitational wave astronomy may one day allow us to detect the subtle imprints left by binary interactions within planetary nebulae, offering a new window into their hidden dynamics. Beyond their scientific value, the ethereal guardian formations continue to inspire philosophical and artistic interpretations. Their resemblance to eyes, portals, and celestial symbols has captivated the human imagination for centuries. Whether seen as the eye of God, a cosmic watcher, or a gateway to the unknown, these nebulae serve as reminders of the universe's vast and intricate beauty. They illustrate the cyclical nature of existence, where even the death of a star contributes to the formation of new worlds. Ultimately, the study of the astronomical sentinel reinforces one of the fundamental truths of astrophysics: the universe is in a constant state of transformation. Stars are not isolated entities but part of a vast cosmic network, where their births, lives, and deaths influence the evolution of galaxies. Every planetary nebula we observe today is a glimpse into this ongoing process, a snapshot of stellar material returning to the cosmos, ready to begin anew. As humanity continues to push the boundaries of space exploration and cosmic understanding, the celestial sentinel stands as both a scientific treasure and a poetic reminder of our place in the universe. Each discovery brings us closer to answering the fundamental questions of our existence. Where did we come from? What will become of our sun? And how do the echoes of dying stars shape the fabric of space itself? With every new observation, the spectral guardian continues to reveal its secrets, guiding us deeper into the mysteries of the cosmos. The ethereal watcher, embodied in the grandeur of planetary nebulae, serves as a celestial archive of stellar evolution, a testament to the transformation of the universe across cosmic time. As these formations drift through the vastness of space, they offer not only a glimpse into the past but also a predictive model for the fate of future stars, including our own sun. One of the most fascinating aspects of the cosmic eye is its role in the feedback mechanisms that shape galactic structure. While often considered mere remnants of stellar death, planetary nebulae actively contribute to the ongoing evolution of their host galaxies. The gas and dust they expel enrich the interstellar medium, seeding future generations of stars with heavy elements. This process, known as chemical enrichment, is crucial for the formation of rocky planets, complex organic molecules, and even the conditions necessary for life. The study of the astronomical guardian has revealed that the dynamics of these nebulae are far more intricate than previously thought. Early models depicted planetary nebulae as simple, spherical shells of gas expanding uniformly into space. However, modern high-resolution imaging has uncovered a surprising diversity of shapes and structures, ranging from symmetrical ellipses to highly complex, asymmetric formations. Some nebulae display elongated lobes, others feature intricate filaments or even helical spirals, suggesting that multiple factors influence their morphology. One of the key drivers of these variations in the spectral sentinel is the presence of binary star systems. When a dying star has a close companion, gravitational interactions can significantly alter the shape of the resulting nebula. In some cases, the secondary star can siphon material from the primary, creating dense equatorial rings or spirals of gas that persist long after the initial ejection event. Observations of nebulae such as the Southern Crab Nebula and the Red Rectangle Nebula have provided compelling evidence that many planetary nebulae owe their distinctive appearances to binary interactions. Beyond their structural complexity, the galactic observer also plays a key role in astrophysical chemistry. Infrared spectroscopy has revealed the presence of complex organic molecules within planetary nebulae, including polycyclic aromatic hydrocarbons, PAHs, and fullerenes, carbon-based molecules shaped like spheres or tubes. These molecules, often associated with the building blocks of life, suggest that planetary nebulae serve as cosmic laboratories where the raw materials for planetary and biological evolution are forged. Their presence in nebular remnants reinforces the idea that organic chemistry is widespread throughout the galaxy and may be a fundamental component of planetary formation. Additionally, the Celestial Gateway is an ideal laboratory for studying the physics of radiation-driven winds. The interaction between the central white dwarf's intense ultraviolet radiation and the surrounding gas creates ionization fronts that propagate outward, sculpting the nebula's structure over time. These processes are responsible for the bright, glowing edges and intricate internal patterns observed in many planetary nebulae. By studying these interactions, astronomers gain valuable insight into how stellar winds shape not only planetary nebulae but also the larger interstellar medium. Recent advancements in computational astrophysics have allowed researchers to simulate the formation and evolution of the universal sentinel with unprecedented accuracy. These models incorporate factors such as fluid dynamics, radiation pressure, and even magnetic fields to predict how planetary nebulae develop under different conditions. The results of these simulations have been strikingly consistent with real-world observations, confirming that planetary nebulae are shaped by a complex interplay of forces rather than simple expansion alone. The future of planetary nebula research is poised for dramatic advancements with the next generation of space telescopes. Instruments such as the James Webb Space Telescope, JWST, and the upcoming Extremely Large Telescope, ELT, will provide astronomers with deeper insights into the fine structure and chemical composition of these nebulae. With their enhanced sensitivity, these telescopes will allow scientists to probe nebulae at higher resolutions, tracing the flow of matter on scales previously unattainable. Moreover, the study of the heavenly sentinel has profound implications for understanding the fate of our own Sunday. In approximately 5 billion years, our star will enter the red giant phase before expelling its outer layers and forming its